Okay, this is one of those ones where I'm going to talk about it because I kind of found this out and then I was just thinking about it. I just couldn't stop. I couldn't stop just like being so baffled and in awe of the fact that um, pendulums the way pendulums work, right? And I never really thought about it. There's so many things that you just never think about, right? It's just there. And so, you look at like old clocks for like a grandfather clock or, whatever other kind of clock. A lot of them run off of pendulums. I never really understood how that worked, right? Because I was like, doesn't that like just like stop like super fast? Like, how does that motion keep going? Like, where is it? Like, does it keep putting in energy to like keep that swing going? Like, I didn't really understand how the clocks worked and what the pendulum mechanism was doing. And I knew that it was a part of a clock and that clocks use pendulums, but I didn't understand really why, and I didn't really understand, the significance at the time, right? So I'm watching some video, and it's casually just said, "Oh yeah, pendulums, they rock back and forth in they take the same amount of time, like the period between swings is consistent." Regardless of how far it goes, like it takes the same amount of time regardless of how far it goes, so long as it's in a small angle uh, of like oscillation. Obviously if it's in a large angle of oscillation, it's not as precise, right? But after a certain point, there's a certain point, I don't know if I might have gotten where that actual angle is. So, a relative estimate, it's considering a small angle as anything less than about 10 degrees, right? So, a pendulum will rock back and forth if it's within that 10-minute, well, technically that is a term for degrees, but 10 degrees of angle from from straight down the vertical. So if it's in the vertical, 10 degrees up and you let it go, it'll rock back and forth, and over time, yes, it's going to lose energy, so it's not going to go up as high as it started, right? And it's going to slowly work its way down. But during that time, as it's slowly losing, distance, right? It's going a shorter distance. You would expect that it would get faster, right? But it doesn't. It doesn't get faster, right? No, it keeps that same interval of time. So say it takes 1 second for it to get from here to here, then for it to get from here to here is still 1 second, and from here to here is still 1 second. And it's just one of those things that I feel like is taken for granted because it's not really something that I ever really thought about. And it sounds so stupid. It's like, well, yeah, but it's like, but I just think that is so crazy, right? Because basically what that is temporal stability, right? So we imagine that it's like there's another video, it might be another talk, but there's like time crystals where we found out that we can input some energy into these time crystals and they will oscillate back and forth, right, in a pattern, in a regular motion. I think it's in a set time length as well, right? And so in a certain amount of time it'll oscillate back and forth, and so we've created quote-unquote time crystals. Pendulums are basically an upscaled time crystal is what I'm trying to say here. I think. I don't know. And I just think it's so crazy that after a certain amount of energy is lost, right? Because it's not always even, right? There's a certain limit where then it falls into this point where it is now in this equilibrium. And it's not like, oh, it's, it's accurate from 10 degrees to 4 degrees, and then after that it falls off and it doesn't work anymore. No, all the way down to, quote unquote, zero motion, right? And what really makes me, kind of get it, really thinking about this is like, okay, well, if after 10 degrees, right, then the period stays the same. Well, we think, like, at a certain point, our eyes, we look at this pendulum and it's no longer moving. And maybe it really is no longer moving to all observers, depending on, like, it doesn't matter how much you zoom in, like, no, it really did stop moving. We assume it stopped moving. Maybe every still object behaves on this same mechanic, is what I'm trying to say. Because what if this pendulum we think has stopped moving is still oscillating in this temporal stability, right? It's still moving 1 second. It's still moving that same oscillation period every second, right? So it's moving through time every second. So everything that's standing still is moving through time at 1 second per second. But to us, we perceive that as not moving at all because everything's moving at 1 second per second. And so I like, because I was thinking about it, like, pendulums, like, they eventually stop, but they still, like, do they, right? And I don't know. I just think that it's so cool because pretty much the fact that it's not always true, right? It's not always true. It's after a certain point, right? Then it starts to fall into this period. And what's happening is that it doesn't matter how much energy you started with to begin with, it will always come back to this point. And what is that? It's a rest point. It's the point of lowest energy, right? But the thing is, there's still enough energy to maintain that temporal stability at a certain point, right? Like, I feel like I'm talking, like, no one's gonna understand what I'm trying to say here, but it's so, like, it's so crazy because it gets into that quote unquote extra dimension of time that we can't perceive, but maybe we can. We haven't realized it yet, right? Right? We haven't realized that we're perceiving it all the time, right? I mean, obviously we're perceiving it all the time because time is passing and we notice time is passing. But the way we observe time passing as, oh, it's just it's just kind of doing that, right? And it's not just this passive thing that's around us. It's a whole another, I don't know where I'm going with that. All right. It's crazy, right? Because you can put in, like I said, however much energy you want, but that energy will slowly drain out, right? That energy will slowly drain out. And over time, it will come into this certain equilibrium point. It'll come into a point of balance, and it will maintain that period of oscillation, right? And the period of oscillation is what's key, right? Because it's not the motion, it's not the distance of the motion that matters, it's the period of the oscillation, right? Because the thing is that the thing is that, like, you are applying this energy in, right? And that is on our, dimension. This is on our level of energy, our physical reality, right? So we apply this energy in, but that energy is excess energy. That energy is, applied energy. It's relative energy. It's not its quote unquote rest energy, right? Everything has a rest energy, and that rest energy is based off of its mass, right? But maybe that mass gets its rest energy from, because I'm like, well, what even is mass, right? What even is mass, right? And so maybe this place that this rest energy is coming from, right, is sourced from basically time itself. Because as I said, time is energy, right? And so there is an ambient level of time energy everywhere that allows things to oscillate at a certain period, and that is why time can travel at different rates, because depending on the amount of energy that's there, things can oscillate faster, right? And if they oscillate faster, they move through time faster, right? And so that is where we get this time relativity from, like a certain next level scale. And it's so hard to understand. It's so hard for me to know if I'm getting my point across accurately, because I barely even understand what I'm talking about myself. And it's so hard to picture this, because it's like, it's not something we're comfortable with. It's not something that we experience and we are aware of. It's not something that we actively observe. But a part of me thinks that maybe we do, and we just don't realize it, right? We haven't been, you know, it's kind of like you can see things in your peripheral vision, right? But you don't actually see it in detail until you actually look at it, right? It's been there, it's all there, but you have to actually look at something in order to get the details, in order to actually understand what you're looking at. Because you can see kind of like faint colors and things here, but you don't know exactly what it is until you look at it, right? And I think maybe that's what time is. Like, you know, maybe we can get a better understanding of what time is than we actually think that we can, right? Maybe it's not as far outside of our limitations as we thought, is what I'm trying to kind of get across with this video, I think. Yeah, I don't know if I ever finished this thought, but you know, you can put in as much energy as you want, right? And it's almost like, you know, in theory, you know, the planets have aligned themselves into these points of equilibrium, these points of stability. They are in this point of, you know, oscillation, you could basically say, or rotation. I think that both of them are synonymous, because I think rotation is basically the core principle of everything, which is why circles and pi and all that stuff is so prevalent in everything, because circles and, you know, oscillations is just how all interactions happen. But I am going to move on from that. So basically, the planets are in these points of equilibrium. They're in these points of balance, right? All the planets are sitting in relative, maybe not in the precise points, but they're pretty darn close to these points by this point, right? By this far into, you know, the creation of or the evolution of our solar system, right? You know, in order for the planets to last as long as they have, they had to fall into points of stability, because if they didn't fall into points of stability, by this point they would have either, you know, been flung away, or they would have fallen into the sun or something, right? Like the planets didn't necessarily form where they are currently, right? But they slowly, depending on what their mass was, moved into that position. And once they found that equilibrium, that's where they stuck, right? And so what I'm trying to say is that with this pendulum is that we started at a point where it's not at equilibrium, but eventually it will find it. And once it finds that point of equilibrium, it's stuck there. It does not escape. Without you applying more energy to it, it does not leave. None of the planets are going to leave the solar system without something applying energy to them, without them being affected by something else, right? Because their internal energy is not enough for them to be flung away or move anywhere, right? And so there may be some slight shifting still happening, and there may not be totally set into these quote unquote equilibrium points, but I believe that they should be all relatively close to them. And this gravitational equilibrium that we're seeing with orbits of planets in our solar system, I think is something we can translate to temporal stability, right? And so it's kind of hard to imagine what exactly this oscillation or this rotation is that is taking place, because what's weird about four dimensions is that we're looking at a pendulum slide back and forth, right, in a 3D universe. And to us, we're saying, oh, well, it's just moving back and forth. But in a 4D universe, it's doing this, right? In theory, all right? In theory, it's doing this. It's going in a circle in the fourth dimension, and to us, it appears as it's just going back and forth. Because look at what my hand's doing. It's just going back and forth to you, right? Because you're looking at my hand in 2D now, right? And so to you, it really looks like my hand is basically just going back and forth, right? But it's also, going in a circle. And so I think that a pendulum is basically doing that. It's basically doing that, right? And so it falls into this point of temporal stability where it's locked into, this certain, rotation speed. But that's on the fourth dimension. In our dimension, right? Or like basically our reality. In our reality, right? It still has that relative energy, right? Because that's its rest energy, but it still has relative energy. Because remember, if you watch my other videos, right, I talk about how there's the rest energy and there's the relative energy, and basically rest energy is comparable to like E equals mc squared, and then the relative energy is the actual velocity, right, that you would measure, which is everything. So basically, in other words, everything is moving at the speed of light, in theory. Everything is moving at the speed of light. However, we can also add on additional velocity to everything. But that velocity is not real in all respects, because depending on the velocity of whatever you're measuring it from is going to give you a different answer for the velocity of this, right? So if this is flying at 5 miles an hour and you're at 5 miles an hour, you're at rest, right? They're both at rest. But if you're at 10, then this one is flying and this one's flying at 5. Like, in theory, this one's actually flying at -5. Like, it looks like it's flying away from you, even though you're actually you're flying away from it, right? And so depending on your relative energy, your velocity, it changes what the relative velocity is for this, right? And so that is how we kind of relate it to gravity and our reality, right? That is my tie-in there. But now we're imagining, okay, so we have the rest energy, right? But it still has its, relative energy. And this might be something entirely different, but like the quote-unquote rest energy that I've been talking about in the temporal space might be something completely different, and you could potentially take the rest energy of what we would consider, E equals mc squared, right? So we have the equation E equals mc squared plus, E equals mc squared plus mv squared, right? So that's the quote-unquote equation. That's not how it's generally written right now, but that's how I think it should be written. And so this mv squared is the relative energy, right, for our universe, right? And then there's the E equals mc squared, or just the mc squared portion of that, right? So that's the rest energy, right? And that comes from basically just the fact that everything has mass and therefore everything has innate energy. And maybe we can potentially break this term down or just redefine, where that, like, I think potentially we could split this term up again into another relative, like a relative mass, maybe. I don't know, maybe like a relative mass, right? Where we have like m squared v cubed or something. Like I don't even know exactly, but you would potentially break up this rest term into other terms, and one part of that will be, the temporal rest, right? And then you have the relative, the temporal relative energy, and then you have outside of that, the relative velocity, the relative energy, in the spatial dimension, I guess. I'm trying to explain things that I barely even understand myself here. All right, so cut me some slack. But I would imagine you would have to do something like that. And so, right, so we have this rest time energy, but then there's still, long story short, like I really went on a tangent, but basically what I'm trying to get back to is, even though the pendulum, is oscillating at 1 second per second, it is, moving in, right? And that's because it has its quote unquote rest energy, which is set at this 1 second per second, or like one, like 1/2 every second or whatever, like, or one like rotation every second or half a rotation every second, right? So it's set at this like this rest point, right? So it found its equilibrium orbit. But to us, we see that orbit looks like it's shrinking, right? And so to us, it looks like it stops, but it's really just that it's not that it stops. It's just that it finally reached the point of zero. Maybe it's not even zero rest energy, but it's just zero, relative energy, right? Because now its relative energy is zero because it's not moving, right? But if we wanted to break down that relative energy, I still stand by that you can split that up. Most likely you can split up the rest energy based off of mass and the speed of light. You could probably split that up and to get some kind of temporal thing, but I don't know what that would look like exactly because I just don't at the moment, at least. And so, if it slowly, like it finally reached its rest, like it reached that point of like equilibrium with just whatever. Like it's so hard to say, but basically it's like the temperature of the room, right, is constantly fluctuating in theory, right? But if you let a room sit for long enough, the entire room should become relatively uniform. Is it going to be exactly uniform? Maybe not. Like where that gets into what kind of scales are we measuring at? Is it every cubic centimeter? Is it every cubic like picometer or something? Like that gets a little ambiguous. But in theory, in like for practical reasons, the room is a uniform temperature, right? So the room has become this uniform temperature. And so it's no longer moving, right? But like that's just like if you put energy into it, right? You send in like a burst of hot air. All right. Now there's this point that has more energy than everything else, and so it needs to be balanced out, right? And so everything in the room then rebalances, and then it slowly comes back to equilibrium again, right? And so I think that everything looks stationary and time is relative, basically based off of the quantity of time. And I know that that sounds so ridiculous because it's like, what do you mean the quantity of time? And I don't know exactly, but you know, the temperature of the room is based off of the amount of energy in the air, right? It's not like a physical thing. It's just the amount of energy in the air. So if you wanted to reduce the temperature, you have to reduce the energy. And so if you want to slow down time, you have to reduce the amount of time in the room. And if you want to speed up time, you need to increase the amount of time in the room, right? And that sounds ridiculous because we don't see time as this sort of 3D spatial dimension. We see it as this +1 on our 3, you know. We don't see it, we see it as this thing that you can only go in one direction in, and you know, the reason for that is because gravity only goes in one direction, you know, like it doesn't just kind of, you know, change which way it's going. It's always towards the mass. It's always towards the mass. And so time always flows in one direction, just like gravity, because they're functioning off of the same principles, which is high energy flows towards low energy, which is entropy. And like, that's just what everything does. That's just what everything does. All right. Don't ask me. All right. But, yeah, I mean, like, I don't know what I've not said at this point, because this has gone quite long, but, that's one that I felt like I really needed to make sure I put out there, just so someone else could chew on that and potentially, you know, refine it. Because I don't think that that's in my scope of work. You know, if it becomes a part of my scope of work, I might have to request a change order. But, you know, it was a thought that it really just stunned me when I started thinking about it. And I didn't even like read any of what I wrote down, but I don't think I need to. Because I think I got it. Yeah, I don't know. I'm pretty confident that in my rambling, I covered everything. So, yeah. Peace out.